So in the notes for today for 20.2b, we're going to be looking at line plots. And so line plots defined right here. It says that a line plot is a graph that shows the frequency of data along a number line. You're not going to use it when there's a lot of numbers. It says it's best to use it when comparing fewer than 25. Otherwise, I don't know, it just kind of becomes too much to look at all at once. So that's the kind of graph that we're looking at today. The frequency of an event is defined as being the number of times the event occurs in a study or a survey, or the number of times the data value appears. And so looking down here at this first one, sometimes when you do line plots, you'll see them represented like this with X's. Sometimes you'll see them with dots, or they could have other symbols as well. So when you look in the list of numbers, the little two X's that show up right here on top of the number 1 means that in the list of numbers, there were 2 number 1s in the list. And then so on. 1, 2, 3, 4 X's stacked on top of the number 2 means that in the list there's 1, 2, 3, 4 number 2s in the list. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 number 3s. There should be 4 number 4s. 1, 2, 3, 4. And then lastly there should be 2 number 5s. 1, 2. The number of X's, or the number of symbols on your line plot, correspond to the number of values in your data set. So when you're all done, you should be able to count all of these up and make sure that it matches the number of numbers that are in your list. And again, the total number of X's or symbols that are used to represent the values represent the frequency. Notice how when you stack them kind of nicely, so you can look at the height for how tall they are to compare how many of them there are. So there's 2 number 1s and there's also 2 number 5s, and you see how the X here is kind of equal to the X here. That's helpful to notice as well. So when you make your own line plot, you're going to draw a number line. It's important that the spaces are approximately the same distance away from one another. You want to look at your data values to figure out what numbers you want to count by. So on these ones, the numbers are all pretty close together. It looks like the least number in my list, like my minimum value, is right here. It's my number 4. And then it looks like the biggest number in my list is this number right here. It's the number 12. So I have to count from 4 to 12. And if I start with 4, that'll be plenty. And so on this one, I'm going to choose to count by 1s, but on a different graph, you might choose to count by different numbers. Now, every time I see a number in the list, I'm going to draw an X and I'm going to stack it up. And you can either do the numbers one at a time, or you can look for all the 4s, then look for all the 5s, then look for all the 6s. It works both ways. So there's 1 4. I'll use X's in mine. When I look through the list, there's no number 5s. And then there's 1 number 6. And then I'll look for the list through my 7s. There's 2 number 7s. And then there's a bunch of 8s. There's 1, 2, 3, 4. There's 4 number 8s. So again, you want to try to stack the X's so that they're approximately equal to each other in terms of their height. It looks like there's 2 number 9s. There's 1 number 10. There's no number 11s. And then there's 1 number 12. And so this line plot represents what's going on in the previous question. You can use line plots to answer questions about frequency. So for example, in this case, 8 is the most common age because there's the most 8s in the list. So on B, our smallest number in the list is 66 and our largest number in the list is 80. So those are my minimum and my maximum. And so on this one, I'm going to start counting at 66. If I drew the 67 and the 68 and the 69 and the 70 and so on, my numbers might look kind of squished on my paper. So what I'll sometimes do is I'll skip count by 2s, so 68, 70. So each line is still representing one value on the paper, but this is just helping me a little bit because it's like less numbers to try to squish in. So this represents scores on a test. And so again, when you go through, you can either put the X's, like you could put an X on 80 first and then put an X on 78 second to represent those frequencies, or you can go from smallest to greatest. So it doesn't matter either way you do it. There's 166, there's no 67s, there's no 68s, there's no 69s, there's 170. Remember, you want those X's to be level with one another. There's no 71s or 72s or 73s or 74s, but then there's 275. See, there's 276s, and then there's 1, 2, 3, 4 77s in the list up above. There's 178, and then there's no 79s, and then there's 180, and that should finish us off. A really nice idea when you're all done is you can go back and count the number of X's and then count the number of numbers in your list to make sure that you didn't miss any. In the last example here for the line plot, these represent the salaries in thousands of different employees. So just think about it. 35 doesn't mean 35, it means 35,000. 36 doesn't mean 36, it means 36,000. We're just going to put the numbers down here. So let's see, following in our pattern, the smallest number in our list is 34,000, and then the largest number in our list is 40,000. It says it's being counted in thousands though, so when I label it down here, it's okay just to label them as the regular numbers, the way they show up in the list. So you might want to make a note on this one, label the axis. So this is salaries, but they're being counted in thousands. So same thing, let's see, for this one, there's one $34,000 salary, and then there's 1, 2, 3, 4 for 35, and then for 36, there's 1, 2, 3, and then you'll continue on through the rest of this one. So there's 2 for 37, it looks like there's just 1 for 38, none for 39, and then just the last one for 40. When we're going through to talk about how data is distributed, a distribution talks about how the data looks when you look at a graph. Are they all kind of grouped together? Are they all sort of the same? Is there more on the right? Is there more on the left? And so there are 4 different kinds of distribution. You may want to go through and number them on your paper. So uniform distribution is one kind, normal distribution is a second kind. Your data can be skewed to the right or it can be skewed to the left. And so those are going to be the 4 that we generally pick from. In a uniform distribution, if you were to see it graphed, again, they're usually graphed on a number line. A uniform distribution kind of looks like, I guess it's hard to draw it, but it just sort of looks like the data are like level with one another. Like if there were values here and values here and values here and values here, all outcomes are equally likely, means that like if you were to draw a line across the top of it, the line would be pretty much straight, almost like a rectangle. A normal distribution, it says that it looks like it's symmetric, bell-shaped, and a curve. And so in a normal distribution, the most are in the middle, it goes up the hill, and then it comes down the hill. And so it looks like it's equal on both sides, but in a normal distribution, it's higher in the middle. So uniform is the one that looks like a rectangle. Normal is the one where it's highest in the middle. And then there are 2 different types of distributions. It can be skewed to the right or it can be skewed to the left. Left skewed distributions have a long tail in the negative direction on the number line. So in a skewed left distribution, all the data are piled up here, and then it's kind of low over on the left side. And then in a skewed right distribution, it's the opposite. So the data are sort of piled up all together here, and so we'll look at examples of both of these. For this next one, it asks us to identify the type of distribution. And so for this one, if you were going to draw a line across the top of it, it wouldn't be perfect, but the line across the top of it stays pretty level from left to right. And so for this one, we would say that the distribution is uniform. After that, the next thing that we're trying to do is we're trying to figure out the mean, and we're trying to figure out the median. And this is a little bit different than the notes from the other day, because when you answer these ones, to find the mean, you're going to need to grab a calculator. Well, I guess you normally need to grab a calculator for the mean. But to find the mean on this one, you need to add up all of the numbers in the list. So ready? This little x is a number 1 in the list. This little x is a number 1 in the list. This little x stands for a number 2, and this little x stands for a number 2. So in your calculator, when you count these up, you're going to type in 1 plus 1 plus 2 plus 2 plus 3 plus 4 plus 5 plus 5 plus 6 plus 6 plus 7 plus 7 plus 8 plus 9 plus 9 plus 10 plus 10 plus 11 plus 11 plus 12. So you're adding up all of the numbers, but remember, whenever there's more than one x, it means that there is more than one number there in the list. So on this one, when you add them all up, you get 129. And then remember, for the mean, you need to divide by the number of values that were there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So on this one, I'm going to divide by 20. And when I do the division for that one, rounded to 2 decimal places, I get 6.45. When you find the median, it's a little bit different. You could write all these numbers out in a list if that helped you, but when a lot of people find the median from a line plot, they do it like this. So they start on the outside. Remember, if the numbers were in order in a list, you would be doing the same thing. So I cover up one of these and one of these, and then I cover up the other one that's here with one of these two, and then I cover up this one with one of these, and then I cover up this one with one of these, and then this one with the other one of these. 1 and 1, 1 and 1. It's kind of hard to keep track of where you are. 1 and 1, 1 and 1. And so the last 2 numbers that would be in the middle not covered up would be a number 6 and a number 7. And so to figure out the median, it's going to be halfway in between 6 and 7. So you would do 6 plus 7 divided by 2, which would give you 13 divided by 2, which would give you 6.5. So again, for this first example, it had a uniform distribution. The mean was 6.45 and the median is 6.5. On this next example, we're going to proceed similarly in the same way. Remember, to figure out the distribution, you're looking at how does it look like it's arranged arranged or distributed. And so for this one, this curve where it looks like it's the same on the right and the left, we call that a normal distribution. Normal doesn't mean like regular. Normal actually describes the way the data are organized. And then to figure out the mean for this one, you're going to do 3.2 plus 3.3 plus 3.3 plus 3.4 plus 3.4 plus 3.4 plus 3.4, and you're going to keep adding those numbers up in your calculator. So for this one, when you add all those numbers up, you get 70. So there's 20 numbers in the list. And when you do the division for that one, you get 3.5, so that's your mean. And then for this one, you want to go back and you're going to do the median as well. And so remember, for the median, you can cover them up from the outside. In a normal distribution, it's kind of easier to find the median because you're covering them up and they're usually equal. So 1 goes with 1, 2 goes with 2, 4 goes with 4. The bottom 2 on this one go with the top 2 on this one, and so the last 2 numbers in the middle would both be 3.5, and you would average those together. 3.5 plus 3.5 divided by 2 would give you 3.5. Alright, and so for these last 2 examples, for C and for D, we're going to do the same thing. So on C, it looks like all the data are piled up on the left-hand side of the graph and they're kind of stretched out to the right. So remember from your notes from the previous page, that means that the data is skewed to the right. And then to find the mean, we'll add up the numbers, so 28 plus 28 plus 29 plus 29 plus 29 plus 29 and so on, and divide by the total. And so on this one, it's going to be 623 is what you get when you add up all those numbers, divided by 20. And so for this one, the mean is 31.15 if we round it to 2 decimal places. And then for the median, same thing. You go on the outside, 1 and 1, 1 and 1, 4 and 4, 1 and 1, 2 and 2. So the last 2 numbers in the middle would be a 30 and a 31. So 30 plus 31 divided by 2 gives you 61 divided by 2, which gives you 30.5 for the median. And in the final example on this page, the data it looks like it's all piled up over here on the right, and then it pulls out to the left. So we say that this distribution is skewed to the left, and then we also have to find the mean and the median. 66 plus 70 plus 75 plus 75 plus 76 plus 76, and so on. For this one, they all add up to 904. And then this one, there are 12 data values in the list. When you divide those values, you get 75.33 rounded to 2 decimal places. And then for the median, 1 and 1, 1 and 1, 2 and 2, 1 and 1. So the median is between 76 and 77. And so when you add those up and divide by 2, you get 76.5. So looking back at the previous page, we can answer the following question about comparing the mean and the median. So for a symmetric or a normal distribution, the mean and the median are equal to each other. We did examples up above that will help us answer these questions here. When the data is skewed to the right, so when the data is all piled up over here on the left-hand side and kind of pulled out to the right, if you compare the mean and the median is higher than the median. And then in the final example that we did up above in D, when the data is all piled up over here on the right and kind of pulled out to the left and skewed to the left, if you compare these, the median is the greater of the 2 numbers. So whenever the data is skewed left, the mean is going to be less than the median. In the final example on the notes today, we're going to decide whether we expect the mean to be equal to, less than, or greater than the median. And so these are the 3 choices that we're picking from. Remember that when you're thinking about them, it's kind of helpful to draw the lineup that goes on the top of the data values, just sort of as a guideline to help you answer the questions. And so they want us to figure out what type of distribution each one is, and then say whether the mean would be equal to, less than, or greater than the median. In this first example A, the data is all piled up on the right, it pulls down to the left, and so for this one we can say first that we see that the data is skewed to the left. Because the data is skewed to the left, we don't have to calculate the mean, we don't have to calculate the median, but we can expect that the mean would be less than the median. In the example B, the data is piled up over here on the left-hand side, and then it drops off, or it's pulled, the tail of the data is over here on the positive side. So we say that this data is skewed to the right. And then to answer the second part of the question, we want to refer back to our notes on the earlier on the page. When the data is skewed to the right, you expect the mean to be greater than the median. In example C, the distribution is normal, which you can also call symmetric. And so in this example with a normal distribution, you would expect the mean, again referring back to the previous notes, you would expect the mean to be equal to the median. And then in the final example for D, this one isn't as skewed left as the first one was, but it is still slightly skewed left because the data values over here on the right-hand side of the graph are higher than they are over here on the left. And again, in a data set where the data is skewed left, we would expect that if we were to calculate it, the mean would be less than the median. And that's it. Thanks for watching.